Hello, this video is going to be about optimizers, another step on the road towards bigger models solving hard real-world problems. My name is Mac, and I'm making a series of videos about computer vision, starting from the very fundamentals and gradually moving on towards state-of-the-art models in the field and exciting new developments in perception and Gen AI. So check out my channel. I'll be happy if you subscribe. Also, feel free to comment. Any feedback is welcome to me, and I'll make sure to answer everybody. And now, let's start with the optimizers. First of all, we're going to discuss what is an optimizer, why do you even need one. We'll study the classical approach to minimizing the loss function called gradient descent. We'll discuss what is learning rate and how that can affect speed and quality of the training. Then we will move on to stochastic gradient descent, which is the one that is usually used in training neural networks. We'll discuss some techniques for improving optimizer further, that is learning rate scheduling, momentum, and weight decay. Finally, we'll discuss another optimizer that works slightly different called Adam. First of all, what is an optimizer? In our machine learning classroom, the model is the student and the optimizer is the teacher. Optimizer is responsible for tuning the parameter of the network to make the predictions that we want. There is another way to look at this. Recall that we can consider neural networks as computational breaths. So in here, you can think of this blue square as the input image, then the red squares as parameters. So this layer is a dense layer that takes in inputs and parameters, does some predictions, then that is fed into activation function that takes no additional input. Then output of this layer is fed into another layer with its own parameters and so on. And finally, in the end, we have the output of the final layer. We have our loss function that is calculated using the output of the final layer, which is basically the prediction of the network, and some external data, the labels for our images. We can regroup these nodes in this way. So we can say that everything that is considered a parameter is now part of the optimization. The beauty of this is that we can stop thinking about the architecture of the network and say that optimizer and actually tuning the parameters is completely separate thing, encapsulated, modulated in such a way that it is not really dependent on what is going on in the network. The only thing that we do need from this network are parameters and their gradients. And this is really good from the software development perspective. So we can have complex neural networks, we can have different architectures, convolutional networks, transformers, networks working with audio, whatever. The optimizer does not need to change. So we can sort of write the optimizer code completely separate to our model code. We can make it modular. So written once, the same optimizer can be reused in other types of networks, in other experiments, and so on. And this is how it actually looked like in our code. So when we trained the neural network made of dense layers or convolutional neural network to do digit classification, we only needed something like 3 lines to define the optimizer. So the first line actually initializes the optimizer and passes in the parameters of the network, saying that, hey, optimizer, these are the parameters. You don't need to know about anything else. Then somewhere we have computed the loss. We called loss.backward to compute the gradients. Then, after computing the gradients, we say to the optimizer that, hey, it's time to do your step. It's time to perform one optimization step. the gradients should be ready. They should be there inside the parameters. And then we call 0grad to get ready for the next iteration. So we don't connect optimizer to anything else that is going on in the network. We don't specify what we do during forward prop in optimization. So it's really sort of modular in a sense that these two things, the network and the optimizer, are completely separate. Gradient descent is really an old method of minimizing any function, basically. It was used way before deep learning was even a thing. And it works like this. So imagine we have the function that we need to minimize. Here it's plotted in one dimension. And in this case, the gradient of the function will point towards the growth of the function. And so minus gradient will point towards the potential minima. And so we start in some point P0, we calculate the gradient, and then we try to make a step towards the minus gradient. Then in this new step, in this new point, we compute the gradient again. We look where it points, and then we make another step, and so on, until we hopefully converge to the global minima of this function. In reality, in deep neural networks, we can't really do that, because making this full gradient step to minimize the gradient on the loss function basically means that we'll need to take the entire data set, load it into memory, and then perform this optimization step for the entire data set at once. In practice, that is really close to impossible for big data sets at least. So imagine the famous data set ImageNet that weighs something like 150 gigabytes alone just for the images. And then when you actually make predictions for these images, you will also initialize intermediate layer outputs, embeddings, network predictions, gradients, and so on. And so this total size will be much greater. So we can't really afford doing this optimization problem on the entire dataset at once. So instead what we do is we take random small batches of data, then perform one optimization step on this small batch, then throw this batch away, get the next one, and then perform the next step on the next batch, and so on. So it makes convergence harder, because you can imagine that on every small subset of data, the loss function computed on this subset will be slightly different, which causes the gradients to be different as well. So instead of this neat convergence to the global minima of the entire loss function on the entire data set, you will have this jerky behavior that sometimes leads you away from the global minima of the entire function. But the good news is it actually converges. So this method actually works, and we have seen that before when we trained our own model. And this is affordable in the sense that it doesn't require a lot of memory to train. Another important concept in gradient descent is called the learning rate. So in reality, when we do the optimization, instead of just performing this step toward the gradient, meaning modifying the parameters by the actual value of the gradient, of the minus gradient, we also multiply it by a usually small parameter called learning rate. And we do that because if we don't do that, or if the learning rate is too big, then what will happen is we'll make one step, we'll get somewhere here, then we'll make another step, but then this gradient only shows us basically the slope of the function in this precise point, and it doesn't know what actually happens afterwards. So it can happen that we sort of overshoot, we jump over our global minima that we wanted to find, and so the gradient now points to the right, we jump again, and again we jump over the minimum, and we just keep jumping back and forth, and we'll never approach the actual minimum. So this is the problem if the learning rate is too big. Now, if the learning rate is too small, then this sort of not being able to jump precisely into the minima is pretty much solved. So we can get closer to the minimal point. But then if the loss function looks more like this, instead of sort of converging on this global minima that we were interested about, instead we'll get stuck in this local minima that is actually greater in terms of loss function than this one, and we will not be able to jump out of this hole. So if we had big learning rate, then we would have just jumped out of it. But then if the learning rate is too small, then we're just stuck there. And the smaller is the learning rate, the smaller has to be the hole for you to get stuck in it. So depending on how the loss function actually looks like, small learning rate might not be good as well. This is how different learning rates actually look like in practice. So these curves show learning rate versus, test accuracy versus the number of steps it took to train the model for different learning rates on fashion MNIST dataset, so classifying elements of clothing. The blue one here is learning rate 1e minus 2, so 0.01. Orange one is learning rate 10 times smaller, and the red one is 100 times smaller. And so I can see that the blue one trained much faster than other models. It took much less steps to reach decent accuracy, but then it started to go down. So we should have stopped somewhere here. So the optimal performance of the model was achieved here. Now the orange one took much more steps to properly train, but then the plateau here is achieved with the slightly higher total accuracy. So the final model that we can get from this one is actually better than the blue model. And for the red one, it takes even more time to train, and I didn't even train it to the end, but it might have converged on even better accuracy, or maybe not. So there is a certain trade-off there. And important thing here is that this is test accuracy. So this is not the actual thing the optimizer optimizes for. So the optimizer minimizes the loss function on the train dataset, which should cause the train accuracy to always go up. So if you'd actually look at train accuracy, it will not sort of start to go down after the plateau. It will always keep going up, or at least stay constant. And the thing that happens there is that while it's slightly going up, it basically is caused by the model remembering all the input images, which is not generalizable. So as after certain amount of steps, as the performance on the trained dataset keeps improving, the test accuracy starts to go down. So we know that big learning rate and small learning rate both have their own advantages and disadvantages. So can we have the best of both worlds? Can we have something that has all the advantages of big and small learning rate? Turns out that we can, and there is a technique doing that called learning rate scheduling. So it works like this. You start initially with a large learning rate, allowing the network to train fast, and then to jump over these potential local minima that you want to skip. Then, after a certain criteria is met, the learning rate is reduced, allowing the descent to approach this point we're interested in closer, and then maybe we can zoom in into this area and then reduce the learning rate even further, making it approach it even further. And the simplest way to do that is actually widely used, is to just multiply learning rate by 0.1 every 100 epochs. So we train the network for a fixed amount of steps, then we reduce learning rate 10 times, then we train for some steps again, and then we continue the process. This process actually has an analog in a lot of other disciplines like metallurgy. So in metallurgy, it's called annealing, which is when you heat up a piece of metal, and then after that you cool it down, and the metal becomes stronger than it was before. And it works using similar physical principle. So this is the crystal lattice of the metal. And so initially it might have some defects, some impurities. So in some cases we have some different element that got stuck inside the lattice. In some cases we have the actual atoms of the metal, but they are out of place, and then they cause the entire lattice to sort of deform a little bit. But and this state corresponds to some local minima, meaning that true global minima of the actual energy of the lattice will be achieved if we don't have any impurities at all. So we have this neat crystal lattice with no defects, no impurities. But then to get there, this defect here, this atom that is out of place here, we have to jump over the neighboring atoms somehow. And it takes energy. So to jump over, you have to temporarily increase your energy, and then you can get to the point that is even better in terms of minimization of energy. And so if the metal does not have enough temperature, this doesn't happen. But then if you heat it up, the defects can sort of jump out, they can travel along the metal, and eventually the lattice becomes pure. And then when you cool it off, you would get a stronger metal. So this is how it works in practice. Now this is the graph of test accuracy for a network trained on the actual ImageNet dataset. So this is a huge dataset, over millions of images, around 1,000 classes with high resolution images. So this is the real one. This is the one that actually allows the network to look at real world objects and describe them. And so we start with the learning rate of just 0.1, which is quite high by deep learning standards. The network trains and then sort of plateaus on a certain level of test accuracy. But then we decrease learning rate by 10 times. And so this allows the network to train further. And then we repeat the process. And basically you have this ladder of continuous steps where we approach the plateau when the test accuracy no longer improves. Then we reduce the learning rate, allowing us to go further, and so on. Now, another thing that can go wrong with optimizing can be visualized if we, instead of one-dimensional picture, go to 2D. So imagine that this is the two-dimensional space, two-dimensional surface, and it looks like this mountain with the basin in between the ridges, right? So the true minimum is somewhere where this green arrow is pointing. So basically you have these ridges that meet in the middle, and then in the middle you also have this gentle slope that goes down to the minimum. So if you apply this classical gradient descent to this one, and if you start somewhere here, the major component in the gradient will always point down with respect to this ridge, because the ridge is much steeper. So it will point here, you will jump to the other side, you will overshoot, and now you are on the other side of the ridge. And again, the gradient is dominated by the slope of the ridge itself. So you jump backwards and then you keep jumping back and forth. And you will only slowly move towards the actual bottom of the basin here, because on every point along the way, the actual gradient along the ridge is much greater than this gentle slope of the basin. And so if the learning rate is smaller, then something similar will happen. You will keep jumping back and forth. You will get closer to the basin, and eventually you will get into the basin, and then you will start moving towards the bottom quicker. But it still takes a lot of steps. And so momentum helps us avoid that. So this is how it works. So instead of saying that we update our parameters by just adding the minus gradient multiplied by learning rate, instead we compute this momentum. That is basically just the current gradient plus some parameter multiplied by the previous momentum that we had. So when we just start, the previous momentum is 0, so current momentum is just the gradient. And then after every next step, the contribution of previous momentums, a few steps back, will reduce because we keep multiplying by this parameter mu that is usually below 1. So if mu is something like 0.9, the effect from previous steps will diminish after something like 10 steps. So you'll only have roughly 10 steps from your history contributing to this momentum. And then if mu is 0.999, then you would have something like 1000 steps contributing into current momentum. And the closest physical analogy of momentum is speed, which can be demonstrated really well by just rolling a ball down the hill. So as you can see here, it also keeps sort of meeting these ridges, but instead of sort of jumping from one ridge to another, the ball has already accumulated some speed, which lets it just sort of bounce from the ridge and continue moving in the direction that is actually prevalent on this hill, which is downwards. So it sort of keeps its energy, it keeps its velocity, and the main direction of movement is always downhill, but it can jump out of some holes, it can bounce off the ridge, so it's really faster that way. And so if we look at our 2D picture with the 2D surface that we had before, now with the momentum, it will look something like this. So we also start on the ridge. The gradient still points somewhere on the other side of the ridge. So we jump and we overshoot. But then we have remembered this consistent direction toward the bottom of the basin, because jumping back and forth sort of cancels out the component that points along the ridge. And the component that points down toward the bottom of the basin, it is constant. It is not changing from jump to jump. So eventually it becomes prevalent. And so this means that the descent will be faster, descent toward this bottom of the basin. Another thing that can be thought of as part of the optimizer is regularization. So generally, regularization is limiting the complexity of your model in order to improve the generalizability. So it will actually make it worse in terms of train loss, but it make it better on the test set. It make it more generalizable. That helps prevent overfitting, basically. And so there is a really good example of this from trying to approximate just some function. So imagine that we had y equals 1 divided by 1 plus 25x squared as the function that we try to approximate. And then we try to approximate using just the polynomial of different powers of x. So we have theta 0 plus theta 1 times x plus theta 2 times x squared and so on, up to 38 degrees. So you can imagine that if we had just theta 0, this is basically the horizontal line, right? Theta 1 times x, after adding that, you might have the diagonal line that might sort of look something like this. So it starts to get better at approximating the function. With just linear components, you will not be able to sort of approximate this curvature. So as you add more members here, you would get better approximation. And the red dots here stand for training examples, and white dots here stand for test examples. So, and they sort of come one after the other. And so, since we only see the training examples during training, if we have extreme complex model, what might happen is, like in here, the model did almost perfectly on the train set. So it actually passes exactly through all these points. But because of the complexity of the entire model, the predictions outside of train set sort of exploded. So the model goes to extreme values just between these 2 points. So the loss on the test set is awful. And regularization is basically limiting the complexity of the model. And one way to do that is to just say that we penalize the actual value of the parameters. So we only increase the value of the parameter if the gain in terms of loss function is even greater. That helps prevent the model from getting too complex. So in practice, it can be implemented by adding what is called L2 norm in the loss. So we have our initial loss, which can be cross entropy, for example, and then we add just the square of the parameters, so some sort of scalar that does not depend on the actual, direction, and then we multiply it by some parameter lambda here. So the greater the lambda, the more we penalize the parameters themselves. So this square here penalizes extreme negative values as well as extreme positive values. And so it turns out that when we do the actual gradient descent, this term here, after computing the derivation, just becomes the lambda times the omega I. So instead of doing that explicitly in the loss function, we can just say to the optimizer that we actually want this term here when we perform the gradient step. And this is called weight decay. So the good thing about that is that, again, we can sort of abstract it away from the loss function, from the network, and just say that it is a part of optimizer. Apart from stochastic gradient descent that we've talked about before, there is another optimizer called Adam, which is considered the industry default. So you should start with Adam if you are not sure which optimizer to use. And it actually works similar to what we have seen before. It uses similar concepts, but in a slightly different way. So it also keeps track of the momentum. The equation here is slightly different. So the only new thing here is this 1 minus mu member here. So as this member gets stronger, if you increase mu, then this one becomes weaker, basically. Apart from this, we also have L2 momentum, which is basically the same sort of historical aggregation of squares of gradients. So if L1 momentum is thought of as just speed, as a physical analogy, then L2 momentum is the energy. So the speed has the direction, which becomes really important if you have this jumping from one region to another behavior. And the L2 momentum does not have a direction. So it just shows the overall value of the gradients you have seen in the past. And the actual update rule looks like this. So to get the new parameters on the next step, you get the previous version of the parameters, Then you subtract learning rate times L1 momentum, which is exactly the same we had before. But now in the denominator, you have this square root of L2 momentum plus some parameter epsilon. So the epsilon is usually just a really small parameter needed for numerical stability. And what this causes is that L2 momentum basically represents the effective decay of learning rate. But now, instead of just having a fixed schedule that decreases learning rate in a similar way for all parameters, now this one is per parameter, right? So this gradient square term, it's a vector. So each parameter will have its own version of the denominator that depends on the total value of the component of the gradient with respect to this parameter that we have seen in the past, which might be really useful if the parameters are completely different, right? Because some of them might need big learning rate, some of them might need small learning rate. Having this per parameter decay sort of helps achieve that. And this is how it might look in practice. So basically, we start with the bigger learning rate as we don't have previous history for L2 momentum. Then after doing some jumps, especially if we had to jump back and forth, which causes the total value of energy to accumulate, we now sort of reduce the learning rate just based on the history that we have seen before, allowing us to converge closer to the minima. And that's it about the optimizers. Next up, we are going to discuss the final pieces that we need to train the actual big model to do predictions on a proper data set. And that will be residual connections, batch normalization, and Chi-mean initialization. So stay tuned. See you soon.